So, next application that we will look into is the transmission of data in serial format. Now, as we know that data it has to be transmitted from one computer to another computer or one system to another system, and normally what or maybe one computer to a printer or modem, so like that. Now, while we are doing this transmission, so it can be done in two format, either in serial format or in parallel format. As I already said that the advantage of serial transmission is that the number of lines that you need to draw, so that is less. Okay. So, you have to take only a single line for carrying one bit value, one bit at a time is transmitted, but when you are doing in parallel format, then several bits will be transmitted serially. So, if you are transmitted parallelly. So, if you are transmitting say 8 bits parallelly, then you have to have 8 parallel lines running between the source and destination. So, this is that is why the serial transmission is quite popular in many applications. So, this is simpler and only a few wires are needed. So, traditionally if you look into the computers, they see the serial COM ports or RS-232 ports. So, they need only 3 wires: transmitted data, received data and ground. But there some more controls are needed, which is not stated here for doing the setups and all. So, that is there. Another serial communication is universal serial bus or USB standard. So, that uses 4 wires, 2 for differential data plus power and ground. So, that way this both of them are serial. So, in case of COM port, we need one transmit data, one receive data and ground, and in case of USB we need only 4 wires. Of course, for serial for this COM port RS-232 communication, so more number of lines are needed, but for USB it is 4 only. So, that way USB has become a better standard, but anyway we are looking into the serial transmission. So, traditional serial transmission was slow, but modern system are faster, like USB version 1 is up to 12 megabits per second, FireWire up to FireWire 1 is up to 400 megabits per second, version 2 is even faster. So, now we have got even USB version 3.0, which is still faster. So, that way, but essentially what is happening is that for serial transmission, so we transmit them as a bit pattern. So, this 1 is transmitted as logic high, 0 is transmitted as logic low. So, that way this bit pattern is transmitted serially. Whereas, when higher speed data transfer is required, we need to transfer several bits parallelly, and usually a small number of bytes, each of say 8 bits, they may be moved at a time, and more complicated connections are needed, more wires, and so some applications they will need it. One difficulty with the serial transmission is that since you are transmitting serially, so time needed for the total transmission is higher compared to a parallel transmission. So, it is parallel transmission takes place inside the processor itself. For example, microcontrollers, microprocessors, they can handle in terms of bytes. Inside a computer system on the bus, for example, you are connecting this PCI, we are having PCI bus that connects the processor to other disk drives and all, or SCSI, ID disk drives, and they are all having this parallel communication, but because they were initially parallel because of this thing that this transmission will be faster, but now the serial communication is also being used. Now, interfacing that you have, so from the processor it comes out as a parallel data, but the transmission is serial. So, we need to have a parallel to serial converter. So, these interfaces have changed to serial because it is hard to ensure that all bits on a parallel bus arrive at the same time at high speed of modern systems. So, you are expecting that an 8 bit data, but that 8 bit data, if it is coming through 8 parallel lines, then it is there is a possibility that these 8 parallel bits will not arrive at the same point of time. So, there may be a synchronization problem between these 8 bits. So, it is better that we go for a serial communication where this transmission will be done serially. And also there are other effects like crosstalk between the parallel lines, which affects the logic value that you are sending over the bits. Where higher speed is necessary, so we have several bits are transmitted that may be moved at once, and more complicated connections are needed, more wires like inside the processor itself or inside the computer. So, how do you change this serial device to a computer? So, how do we interface external device that transmits serially with the bus of a computer that transfer only word bit. So, this transmission has to be via some shift register, because then shift register only we can do a parallel to serial conversion, and we have already seen that there you can use some sort of UART for doing this communication. So, this diagram actually explains how can we have this parallel to serial conversion. So, parallel data is loaded parallelly onto these D flip flops, and then these D flip flops are otherwise connected in a series fashion. So, this logic we have seen previously, parallel in serial out type of register configuration, or this is known as PISO structure, parallel input serial output type of structure. So, we can also at the receiving end, so we can have this SIPO structure, serial input parallel output type of structure, where the serially the bits will be coming and then they will be converted into parallel data and given to the processor. Or we can also have parallel input parallel output type of connection. Next, we will be looking into another very important digital circuit component, which is known as counter. So, counters are normally used to count some event. Okay. So, suppose we are counting like so how much time is elapsed from the beginning of certain event, or when the items are moving on a conveyor belt. So, we want to keep a count on how many items have passed through the conveyor belt. So, like that we can have different applications where we need to really count the number of occurrences of events. So, so how do you do it? Like occurrence of an event may be coming as a trigger to your circuit, but the circuit has to memorize like how many such things it has seen. Okay. So, this will be done by means of counters. So, counters are important digital electronic circuits. They are sequential logic circuits because timing is obviously important, and they need a memory to need a memory characteristic, because after every after every event it has to remember how many events it has seen. So, that is why it is a sequential one in nature. And digital counters have the following characteristics, like there will be a maximum number of count, because ultimately the values are stored in some flip flops. So, depending upon the number of flip flops that you employ to hold the count value, there will be a limit. Okay. Like for example, if I keep say 4 flip flops to keep the count value, then after the value becomes all 1, then at the next time instant, when I try to increment this 1 1 1 1 by 1, so it becomes all 0. So, there is a maximum count value which is 15 in this case. The counter may be an up counter or a down counter. So, we can start from some initial value, and the counter may be instructed to increase its value by 1 after each event occurrence, or it may be that we start with some initial value, and then with the occurrence of an event we start down counting. So, this up down counting may be there. The counters may be designed in both asynchronous and synchronous fashion. So, we will see that, and we may have some free running counter or self stopping counter. So, maybe as soon as we power on the system the counter, so it may be it may start running continually without any intervention from outside, or maybe self stopping after the counter has reached a particular final value, it stops at that point. So, depending upon the type of application that we have to choose a particular type of counter. So, in our course, so we will be looking into how to design these different types of counters. The first counter that we will look into is known as asynchronous ripple counter. So, asynchronous counters are commonly referred to as ripple counter, because the effect of the input clock pulse is first felt by the first flip flop, and then it cannot get to the second flip flop immediately because of the propagation delay of the first flip flop. So, it is like this. So, if I have got say if I take say 2 flip flops. So, this is one flip flop and this is another flip flop, then so if so this the clock signal that is coming to the first flip flop, then so the value when this clock signal comes, when the first clock, suppose I have initially made both of them equal to 0. When both of them are equal to 0, Now, the first when the clock pulse comes, so this flip flop makes a transition to 1, but as an input this flip flop sees still the output of the previous flip flop. Okay. At that way, so it will not see this 1 immediately when the clock pulse will be arriving. So, it will still see it as 0, and this flip flop has got a propagation delay. That is why the second flip flop will not see the it will not get the it will not get the 1 value directly there. So, it will not there. So, as a result, the effect of the input clock pulse ripples through the counter, and so we will see how does it operate. Only the first flip flop. So, in the structure that we have to follow, only the first flip flop receive clock pulse from the source, other flip flops receive clock pulses from either Q or Q bar of the previous flip flop. So, what we mean is that if I have got say 3 such flip flops forming the counter, then one possible structure may be like this. The clock pulse is connected to the first flip flop, and the second flip flop. So, the clock pulse is connected from the Q output of the second flip flop. Similarly, for the third flip flop, the clock pulse may be connected from the Q output of the second flip flop. As a result, the clock pulse that so this clock is coming from the outside world. So, when the clock pulse comes, it only the first flip flop sees the clock, rest of the flip flops will not see. When this Q makes a transition from say 0 to 1 or 1 to 0, then only this is being felt by the second flip flop. Similarly, when this flip flop makes a transition from 1 to 0 or 0 to 1, then only this clock will be felt by the third flip flop. So, that is why the last statement that we have here, that this only the first flip flop receive clock pulse from the source or the clock generator, and other flip flops they receive clock pulse from either Q or Q bar of the previous flip flop. So, if we have got this type of connection, then you see suppose this is the free running clock that we have. Okay. So, the clock is high for this much amount of time, then it is low for this much time, again it is high like this. So, it goes like this. So, as per the behavior that we have got, so if we connect this clock to the first flip flop, then due to the delay of the first flip flop, the first flip flop will initially the value was 0. So, it will become 1 after some time, and that time is given by this TPLH. So, that is the propagation time from clock to Q0 of the first flip flop. So, it makes a transition here. For the second flip flop, so it does not see the clock pulse immediately, but what happens is that it will see the clock pulse when this clock pulse to be high, when I have got this Q0 output to be equal to high. So, it will see this here. So, then when this particular Q0 is going low, so it will see that there is a transition in the Q0 line. So, then this fellow will be making a transition, getting Q1 to be high, and after some time though, so this Q2 will become high. So, at this point, so this is Q1 is making a transition from high to low. So, now it will be making a transition like this. So, here I have connected, so in this particular case it is connected that it is assumed that clock is connected to Q0. So, the counter structure that is assumed here is like this. So, this is the first flip flop, this is the second flip flop, and this is the third flip flop. So, this is the clock is connected to the first flip flop like this, and then this second line second flip flop. So, we have got this Q bar output connected to the clock, okay. And here also the Q bar output is connected to the clock. So, you see that at this time this Q naught is making a transition from high to low, that means this Q naught bar is making a transition from low to high. So, that is actually sensed here. Similarly, at this point Q1 makes a transition from high to low. So, this Q1 bar is making a transition from low to high, and that is sensed by the third flip flop at this point. So, that way we can have this connection of this 3-bit counter to get this rippling effect. So, this is the structure. So, what has been done? So, this all the 3 flip flops we have taken JK type of flip flop, and this J and K, so they are tied high. So, you remember that in a JK flip flop, if J and K both are tied high, then whenever the clock comes, so it will make a transition. Now, you see that if this is the free running clock signal that we have. So, this Q0, okay, so this particular flip flop. So, this will transit at every rising edge of the clock. So, initially if the flip flops are content all 0, then at the first clock edge, so this Q0 makes a transition, it becomes 1. Then at the next clock edge, so Q0 will become 0. So, it will go like this. Third clock edge again it will become high. So, it will go. So, Q0's timing diagram is like this. Now, once we have got the Q0's timing diagram, so Q0 bar's timing diagram is just the reverse of this. So, whenever Q0 makes a transition from 1 to 0, Q0 bar makes a transition from 0 to 1, and that is seen as the clock signal for flip flop 1. So, this Q1 makes a transition when Q0 goes from 1 to 0, or equivalently Q0 bar goes from 0 to 1. So, it makes a transition here. So, next transition of Q1 occurs at this point. Okay. So, at this point again Q1 makes a transition. So, you see now if you look into this count value, if we say that this Q2 is the most significant bit of my count and Q0 is the least significant bit of my count. So, initially if all these flip flops are assumed to be their content is assumed to be 0. So, initially it is 0 0 0. After the first clock pulse high, so it becomes 0 0 1. After the second clock pulse it becomes 0 1 0, then it is 0 1 1, then 1 0 0, 1 0 1, 1 1 0, 1 1 1, and then there is a mistake, these two zeros should be here. So, it becomes 0 0 0. Now, from this point onwards this is basically recycling. Now, it again generates the same sequence. So, we can say that if we try to look into the behavior of this counter. So, we start with 0 0 0, then at successive clock pulses, at clock pulse 1 the count value will be 0 0 1, at clock pulse 2 0 1 0, clock pulse 3 0 1 1. So, it will go like this till it comes to this step 8 where it is 0 0 0, and now it goes on like that. So, it is a 3-bit asynchronous binary counter. We have got the timing diagram for one clock cycle, that is for one cycle, that is for 0 to 8. So, that is since it is a 3-bit counter. So, after 8 it will be overflowing and it will be coming back to 0, after 7 basically, after 7 it will coming back to 0, and now this sequence will be repeating. Now, you see that this clock signal, if you take it as some event, for example, it may be on a conveyor belt, items are passing and there is a sensor, light sensor, which senses that whether some item is passing or not, and whenever some item blocks that light. So, we have we suppose we have got a 1. Okay. So, that way so this clock signal is generated from that items moving onto the conveyor belt, and accordingly this counter will now be counting like how many times it is getting blocked. Or if we have this circuit in the installed at the door of a room, and we have got appropriate sensors for sensing whether somebody is entering into the room or not. So, every time a person enters or some obstruction occurs, then the light maybe there is a LED and a sensor, and they will be sensing that the light is getting obstructed. Accordingly, that can be treated as an event, and every time that event occurs, so it will generate a pulse like this, and accordingly the count value will get implemented. So, at the end of the day we can have a count about how many persons entered the room on that particular day. So, this way we can have this ripple counter implemented and used in digital systems. We can also have asynchronous ripple counter. So, this is in this case 4-bit, this is a 4-bit asynchronous ripple counter. So, previously it was a 3-bit counter, now we have got a 4-bit counter, where this Q0 is connected to the clock of the Q0 bar. Basically this Q0 and this is inversion. So, that means at the falling edge of the clock the transitions will take place. So, you can reason out in a similar fashion that if you start at time 0, then initially all these contents are 0. Then if you give some clock pulse at the falling edge of the clock, this Q0 will become 1. Similarly, this flip flop will transit at the falling edges of Q0. So, at the falling edges of Q0, this Q1 makes a transition. At falling edges of Q1, Q2 makes transitions. So, like this, and at falling edge of Q2, Q3 makes a transition. So, here also if you look into the pattern, so initially it is 0 0 0 0, then at this time it is 0 0 0 1, then it is 0 0 1 0. So, it generates this particular sequence. So, 0 0 0 0 to 1 1 1 1 and then it repeats the sequence from the state 16. So, this way we can have this 4 bit asynchronous binary counter. Sometimes we do not want to count up to say the maximum capacity. So, if you look into this diagram, so if I put n such flip flops, then you can understand that the count value, if I start at 0, it will go up to 2 to the power n minus 1 and then it will repeat. So, this is the standard behavior. Okay. Now, many times we do not want to go up to 2 to the power n. For example, in a 4 bit counter, we may be interested to count up to from 0 to 9 only, and after 9 we want to come back to 0. So, that is if you are following some decimal system, maybe we may be interested in some counting up to 0 to 9. So, this type of counters, they are known as decade counter, that is it is modulo 10 counter. Okay. So, for getting that type of counter, so we can do some modification to the circuit that we have drawn here. So, modulus of a counter is the number of unique states that the counter will sequence through. Like previously, that was the counter that we had. So, that was a mod 16 counter, because it was going through 0 to 15, 16 distinct states or distinct unique states. And the counter can also be designed to have a number of states in their sequence that is less than the maximum value of 2 to the power n. So, decade counter is an example of that category. So, where we have got up to 10. Okay. So, how can we do that? So, one possible way of designing a decade counter is that after the counter is we want to recycle the counter after 9. So, for that, when as soon as the count value becomes 1010, maybe we can put some NAND gate and then connect it to the clear line. So, this diagram actually shows it. So, when the count value becomes count value becomes 9, after that in the next clock pulse the count value becomes 10, that is 1010. So, when it is 1010, so the combination is so this is the most significant bit. So, this is 1 0 1 0. So, when it comes like this, now what we are doing? We are taking out, so this this one here and this one here. So, these two are taken. So, they are given to this NAND gate, and so NAND gate output becomes 0 and they are connected to the clear input of this flip flops. And since this clear bar connection, so as soon as this clear line becomes 0, so all these flip flops will become 0. So, their content will become 0. They will become 0. So, essentially what happens is that after this counting 9, when it goes to 10, it immediately comes back to 0. Of course, for a very small amount of time it will show the value 10, that is determined by the delay of this NAND gate and the delay of this clearing circuitry in the individual flip flops. But after that the value will become equal to 0. And if that value is much less compared to the clock duration, then that value may be negligible, but you will get a glitch like this. So, here you will get a glitch, momentarily the value will become 1010 and then value will momentarily become 1010 and then it will be going to all 0. Okay. So, this way you can design, you can put some extra gates. So, whatever count value, whatever mod value is given, suppose I am asked to design a mod 11 counter. Mod 11 counter means 11 in that case, so if it is mod 11, so it is 1011. So, in that case what I have to do is that I have to take a NAND gate where this these connections will be there. So, this is 1 0 1 1. So, these two ones are already there. So, I have to take this one also and connect it as another input to this NAND gate. So, then what will happen is that when the count value becomes 1101 or 1011, then this clear value will come and it will reset the counter. So, that way you can very easily decide this resetting value. So, depending upon the mod value that you have, so you can decide whenever that particular count is reached. So, you can say that okay, I will stop at that point and you can get this decade counter or whatever be the mod value. So, accordingly you can decide the counter. So, you can also design counters in a synchronous fashion. So, previously we have seen the counters which are asynchronous in nature, because the individual flip flops they were not operating at the same clock. So, all the flip flops they had clocks, but the clock was not common throughout the design. But another possible type of design is when the same clock signal is fed to all the flip flops. So, that will give rise to synchronous design. And the synchronous counter design is also simple, like in this particular case what we do, it is a 2-bit synchronous counter. So, there is a the clock signal is connected directly to both the flip flops, but this is the JK line. So, these J and K lines are tied high for the first flip flop 0, and for the second line J and K. So, they are tied together and connected to the Q0 line. So, whenever this Q0 equal to 1, then only this J1 and K1 they get the value 1. So, as a result this flip flop will toggle. So, if you look into the timing diagram, you see that the first flip flop Q0, so it toggles after at the rising edge of every clock, okay, because this J and K are tied high. So, they are actually doing the transition at the rising edge of the clock. On the other hand, this second flip flop, the flip flop 1, it makes a transition whenever Q0 is equal to 1. So, at this point Q0 is equal to 1. Now, when the clock signal comes, so at this point Q1 does not make a transition, because Q0 was equal to 0 at that time. Now, so it could not make any transition, but at this point Q0 was equal to 1. So, Q1 makes a transition, so it becomes 1. So, after then again at this clock edge Q0 is equal to 0. So, Q1 does not transit, but at this point it will again transit. So, if you look into this value that it is counting, so it is 0 0 here, then it is 0 1 at this point, then it is 1 0 at this point, and then it is 1 1 at this point, then it is again going back to 0 0. So, that is a 2-bit synchronous binary counter. So, in this way we can design synchronous counters also. It is not mandatory that the counter should be asynchronous in nature. So, we can design synchronous counters also. The advantage with the synchronous counter is that the problem of glitch will not be there. So, asynchronous circuits, so we have those that glitch, but in synchronous situation, since we are bothered about changes only during the clock boundary. So, only when the clock edge comes the circuit will transit, the flip flops will transit. So, the glitch problem will not be there. So, that is the advantage, and many of the counters are designed in a synchronous fashion.